How does a computer understand something like temperature or pressure? After all, computers are digital, but the world around us is analog. Let's break it down. Welcome back to Masoud the electrician. Computers and processors only understand binary, ones and zeros, but the world we live in is full of continuous analog values, like temperature and sound. To bridge this gap, we convert these analog variables into digital signals using sensors and analog to digital conversion. To read analog values, processors rely on sensors. For instance, a temperature sensor measures heat and generates an electrical signal proportional to the temperature. Similarly, a pressure sensor might detect the liquid level in a tank. Sensors typically output an analog signal, such as voltage or current, to transfer their measurements to a controller. The choice between voltage and current depends on the application and environmental conditions. Voltage signals, such as 0 to 5 volts or 0 to 10 volts, are widely used because they are simple to implement and easy to measure. Voltage signals are especially useful in systems where distance between the sensor and the controller is short, as voltage can drop significantly over long cable runs due to resistance in the wires. However, voltage-based systems can be more susceptible to electrical noise, which can distort the signal. Current signals, such as 0 to 20 mA or 4 to 20 mA, are preferred in industrial applications, especially where the sensor and controller are separated by long distances. Unlike voltage, current remains consistent even when the wire length increases or resistance changes, ensuring accurate readings. Additionally, current signals are less affected by electromagnetic interference, making them more reliable in electrically noisy environments. The 4 to 20 mA current loop is an industry standard for analog signal transmission, and it offers several advantages over other ranges like 0 to 20 mA. The first advantage is live zero detection. In a 4 to 20 mA system, a current of 0 mA indicates a fault, such as a broken wire or a disconnected sensor. The 4 mA baseline ensures the system can distinguish between a valid low reading and a failure. Secondly, many sensors can be loop-powered, meaning they draw their operating power directly from the 4 to 20 mA signal loop, simplifying installation and reducing the need for separate power supplies. And finally, high accuracy. The range provides sufficient resolution for most industrial applications while minimizing the risk of signal degradation over long distances. 4 to 20 mA signals are less likely to misinterpret small currents caused by electrical noise, as they don't rely on 0 mA. The decision to use voltage or current signals often depends on the specific requirements of the application. For example, in short distances and low noise environments, a 0 to 5 volt or 0 to 10 volt signal might be sufficient. For example, a temperature sensor in a lab setting connected directly to a nearby controller. On the other hand, in long cable runs or high noise environments, a 4 to 20 mA signal current loop is preferred to maintain signal integrity. Imagine a pressure sensor monitoring a pipeline. If the sensor is located hundreds of meters away from the controller, a 4 to 20 mA signal would be ideal to avoid signal loss and interference. Ultimately, the choice of signal type depends on factors like distance, noise, required accuracy, and the specific characteristics of the application. In either case, proper shielding and grounding of signal cables are essential to minimize interference and ensure accurate readings. Analog to digital converters, ADCs, are the key players here. An ADC samples an analog input signal at specific intervals and converts it into a digital value. This process allows digital processors to understand and work with continuous, real-world signals. The resolution of an ADC is one of its most important characteristics. It defines how finely the analog signal can be divided into discrete digital steps. For example, a 12-bit ADC divides the input signal into 4096 levels. or a 10-bit ADC provides 1024 levels. Similarly, an 8-bit ADC divides the input signal into 256 levels. The higher the resolution, the more precise the digital representation of the analog signal. For instance, in a 12-bit ADC measuring a 0 to 5 volt input range, the smallest detectable voltage step, known as the least significant bit, would be 1.22 mV. Another critical parameter of an ADC is its sampling rate, which determines how many times per second the analog signal is measured and converted to digital. Higher sampling rates are needed for fast-changing signals to accurately capture their behavior. Consider measuring the temperature of a process. A 12-bit ADC with a 0 to 10 volt range connected to a sensor can detect tiny changes in voltage output from the sensor, ensuring precise temperature monitoring. On the other hand, an 8-bit ADC might be sufficient for simpler tasks like monitoring whether a threshold temperature has been exceeded. By selecting the appropriate ADC resolution and sampling rate, engineers can ensure their systems capture the necessary level of detail without unnecessary complexity. When controllers need to output an analog signal, they use digital to analog converters. A DAC takes digital instructions from the processor and converts them into a smooth, continuous analog signal. This is essential for controlling devices like motors, valves, or other equipment that operate with analog inputs. Just like ADCs, DACs have a resolution that determines how finely they can represent the analog output. For example, a 12-bit DAC divides the output signal into 4096 steps. The higher the resolution, the smoother and more precise the output signal. If we are using a 12-bit DAC to control a 0 to 400 volt output, the smallest steps of the voltages, also known as the least significant bit, would be 0.098 volt. This means the DAC can adjust the voltage output in increments of approximately 98 millivolts, providing fine control over the output signal. Similarly, if we used an 8-bit DAC for the same 0 to 400 volt range, the resolution would be much lower, 1.56 volt. This highlights how a higher resolution DAC enables much finer control over the analog output. The sampling rate of a DAC determines how quickly it can update the output signal. In some cases, the output from a DAC might appear as discrete steps, particularly at lower resolutions. To create a smooth waveform, the signal is often passed through a low-pass filter to remove abrupt changes, mimicking a continuous signal more effectively. DACs can output either voltage or current signals, depending on the application. Voltage output is used in applications like controlling a voltage-controlled amplifier or providing an input signal to another system. Current output is common in industrial control systems where the signal must travel long distances without degradation. In the real world, many physical quantities are analog in nature, meaning they vary continuously and require sensors to measure them. Let's dive into some common parameters, the sensors used to measure them, and how these measurements are taken. To measure temperature, we use sensors like thermocouples, resistant temperature detectors, or infrared sensors. Thermocouples work by generating a voltage based on the temperature difference between two junctions, making them ideal for high-temperature environments. RTDs measure temperature by correlating the resistance of a platinum element with the temperature. They are precise and reliable. IR sensors, on the other hand, detect infrared radiation emitted by an object, which allows for non-contact temperature measurement. Pressure sensors include pressure transducers and piezoelectric sensors. Pressure transducers convert pressure into an electrical signal, often using a strain gauge. Piezoelectric sensors generate a charge when exposed to pressure, making them ideal for measuring rapid changes. Weight measurement typically involves load cells, which use strain gauges to measure the deformation caused by a weight. This deformation is converted into an electrical signal. For example, industrial scales rely on load cells to measure the weight of goods with high accuracy. Liquid levels can be measured using radar sensors, pressure sensors, or ultrasonic sensors. Radar sensors send radio waves and calculate the time it takes for the waves to return after reflecting off the liquid surface. Pressure sensors measure the hydrostatic pressure exerted by the liquid to determine its depth. Ultrasonic sensors use sound waves to detect the level. Length and distance are measured using sensors like laser distance sensors or ultrasonic sensors. Laser sensors use the time of flight of a laser beam to measure distances precisely. By understanding the right sensor and method for each application, we can optimize performance and reliability in industrial and home automation systems. Sensors and measurement methods are crucial for capturing real-world data, but what happens next? That data needs to be processed, and this is where analog input modules like this Siemens analog input card come into play. If you've worked in industrial automation, you have likely used or come across modules like this, reliable tools for handling precise measurements. Let's take a closer look at this Siemens analog input card, designed for the S7-1500 PLC. This module is a powerful tool for industrial automation, capable of handling various analog input types and offering high precision. The module has 8 analog input channels capable of measuring voltage signals, current signals, resistance, and thermocouples. The module provides 16-bit resolution, meaning it divides the input range into 65,536 distinct levels. This ensures highly precise readings. For a plus to minus 10 volt input range, the smallest detectable change in voltage is approximately 0.3 millivolt. This module boasts an overall accuracy of 0.3%, measuring reliable performance even in demanding industrial environments. The module includes features like wire break detection and overflow-underflow alarms for enhanced reliability. Users can adjust integration times from 2.5 millisecond to 100 millisecond per channel, balancing speed and noise suppression. This module is ideal for applications requiring precise measurement for temperature, pressure, flow, or any other analog parameter. It supports a wide variety of sensors, making it suitable for industries like manufacturing, energy, and process control. And that's it for today. If this video helped you, give it a thumbs up, share it with others, and don't forget to subscribe to Masood the Electrician. Comment below with topics you'd like me to cover next. Thanks for watching, and I'll see you in the next video.